Thanks. I'll begin with a word of prayer. Dear Father, we thank you for this day. I thank you for the weekend just completed. I just pray that with this day help us to understand a little bit more about how differential equations are applied to the so-called real world. And we just thank you, Lord, that there's a more real world which you are in control of. And we just thank you, Lord, for being the awesome God that you are, Lord. In your name I pray. Amen. I think it's something we fail to think about enough as Christians, but you know, the world that we see with our eyes is just the tip of the iceberg, right? There's so much more going on that we can't see. And I don't just mean quirks. But anyway. Okay, so let me... Alright, let's see here. Where's the magic button? Oh, wait a minute, no. Oh yeah. Let's see here. Now we can discuss our plans for world domination. I love this room. Huh. That door barely fits right now. I wonder how that's going to be in a year. Sorry. So today we'll talk about applications. So I have many applications in mind. So let me just start. Let's see here. I'm in section. Ooh, where are we? .5 of my notes. Let's see here. Ooh, come on. So the first application I would talk to you guys about would just be, physics. So you guys know that m times acceleration is equal to the net force, right? So in particular, what's that mean? That means that m times dv dt is equal to the net force, right? So you can solve this for different different forces using differential equations. Let me show you some examples of that. Let's see here. So example, friction, right? So a velocity-dependent friction force would be something like this. Force of friction is, say, minus b times v. So if the velocity is positive, that means you're going to the right. The friction force points which way? To the left, right? And vice versa. Does this make sense? Right? If the friction force is speeding you up, that's weird, right? I mean, at least I don't usually, I'm sorry, officer, I was just sitting at the traffic light minding my own business, and the force of friction just threw me 100 miles an hour past where you're sitting. I couldn't help it. I don't think they'll believe you, right? And they probably shouldn't. Let's see here, dv dt is equal to minus bv. How do you solve this for b and m constant? So you got yourself like dv over v, right, is equal to minus b over m dt. And when I'm working a physical problem like this, I like to integrate both sides using appropriate bounds. So like this one to v, I would say integrate this from, say, v naught to vf, right? Integrate this from, say, the initial time to the final time. This is and so what's that give us? It gives us the natural log of the absolute value of the final velocity minus the natural log of the absolute value of the initial velocity is equal to minus bt over, minus b tf minus t naught, right, over m. Or if you like, that's the log of the quotient of the final velocity to the initial velocity, right? Times the change in time. And then we can find the initial, we can solve for vf, right? So vf basically is going to be equal to v naught e to the minus b over m times the final time minus initial time by algebra. And then if you want to find the velocity as a function of time here, just set TF equal to t instead of TF, right? And so I have v of t is equal to the initial velocity times e to the minus b over m times t minus t naught. And there you go. That's the velocity as a function of time for a velocity-dependent friction force, using separation of variables to find it. Now, whenever I do a problem like this, I always stop and take a second and count my chickens or whatever, or see where they go to asymptotically. As t goes to infinity, does this make sense? By the way, we're assuming what about m and b? I mean, it's mass, right? Anybody here with a negative mass? Just checking. Okay, so no, right? So as t goes to infinity, what happens to the formula? T not some fixed but arbitrary constant, right? Could be 0, could be 1, whatever. As t approaches infinity, what happens? It's okay. Zero, right? I mean, the e to the minus infinity is 0, right? You guys know this. Sorry, let me stop boring you with these kinds of things. How far does it go during that time? Suppose t dot 0. How far goes, right? So to calculate that, what would you have to do? You could calculate the integral of v of t, right, dt, from 0 to infinity. That would give you the net change in x, right? The total change in x. I think we could actually do that, right? That's the integral v naught e to the minus b over m t dt, right? Which is what? Minus m v naught over b e to the minus b over m t evaluated from 0 to infinity. Of course, that notation, what does that mean? I mean, we're really saying the limit as the upper bound goes to infinity, right? Now, the upper bound there, we have exponential minus infinity again. That's 0. The lower bound's the only one that counts, so what does it give us? So we get m v naught over b. That's how far it goes. Because, again, the upper bound goes to 0. Now, what's another way we could derive that result? Let me show you another way to think about this problem. So differential equations is what you need to solve problems with friction, basically, among other things. So we have m dv dt equals minus dv, right? I did it for v, but you guys could easily see, if I changed v to like v squared or v cubed or whatever, you could still do it, right? It's just different calculus in the middle, right? I mean, there's an open, obvious question there, which is like, what's the real force of friction? Like for your car, what's the dependence of friction on velocity? Do you know? Does that come up in any of your engineering classes? Would that be dynamics? You guys in statics? Yeah, we don't care about friction. Oh, do we care about friction in statics? Equilibria, right? Yeah.
Friction increases with velocity.
Yes. It's complicated, I think. So it's something like the force of friction is something like some coefficient, which is a function of velocity, times v to some power, which is also a function of velocity. The general formula for it is something quite awful, really. That's probably not even sufficient, honestly. I know that for cars, I think for low speeds, it's like a quadratic, like it's minus bv squared, but for higher speeds, it's like a cubic. It's a complicated thing. It varies. It's not easy to pin down precisely. So these problems we do are really they're not I mean, they might appear real world or more real world than some of the other stuff we do, but honestly, they're not really real world. Except that you're doing them and you exist, so they're real world. So don't doubt your own existence. That goes nowhere. So if we want to find the velocity as a function of x, we could do that as well. How do you do that? Standard trick to find the velocity as a function of position, or v equals v of x, as we sometimes say. What you do is it's just a little trick. I rewrite this as m dx dt, dv dx, basically use the chain rule. But what's this? What's dx dt? So we got v dv dx is equal to minus v over m times v. Because dx dt is v, so that's v dv dx. Sorry, I like to say that. And then you can separate variables, right? So, oh, well, that's snazzy. There's a v on both sides. They just cancel. And so we get v is equal to minus b over m times dx, right? And of course, this could be a little bit misleading. So integrate from the initial velocity to the final velocity. Integrate from the initial x to the final x, right? And this gives us vf minus v naught is equal to minus b over m times xf minus x naught. And there you have it. The final velocity is equal to the initial velocity minus b over m times the final x minus the initial x. Or if you write the final x as just x, you could write vx is equal to v naught minus b over m times x minus x naught. But the thing is, it's kind of funny, right? If you ask, like, what's the limit as x goes to infinity, you might be led to believe what? I mean, if you just formally take x to infinity and don't think about this too hard, you're probably led to believe that the velocity is what? X goes to infinity, what happens? This becomes very, very large and negative, right? So v goes to minus infinity. Why is that not a reasonable limit to think about, though? X doesn't go to infinity, right? X goes to this. And it doesn't even get there, right? That's an upper bound on the position. So the limit you're tempted to think about, you actually can't. It's kind of funny. But there is the position as a function, the velocity as a function of position. That's how you do that. So in your basic physics course, of course, this thing looks like m. You know, you have a is equal to a constant, like g, for example. Then you get dv dt, right? So you get equal to g. So then you can do v dv dx, or maybe y, v dv dy equals to g. And so that gives you v dv is equal to g. I should put minus g dy. And so there you get 1/2 vf squared minus v naught squared equals minus g times delta y. And there's that timeless equation that you used in physics. Maybe you remember it, maybe you don't. But we can derive that from the v dv dx trick. Okay, so first of all, we can solve Newton's equations, right? For velocity-dependent forces. Let's see here, what else can we do? Excuse me. All right. That's actually my example 2.52 is what I just did. All right, taking a break from physics for a second. What classroom are we in? Is it science? Yeah. Science. Sorry, it sounds so vague. I guess technically we're in the biology seminar room at the moment, right? So you could chalk this up to biology. Okay, honestly, this isn't all science pretty much. So science is actually a pretty good header. I guess there's an N there, huh? Science. So basically, here's the deal. dN dt is equal to kn. what's this say? It says the rate of change of n is proportional to n with a proportionality constant k. So what are the applications of this? Like n equals to p, population, right? And then if you have k greater than 0 or k less than 0, what's the deal? Growth, death. You talk about death rate or growth rate.
People are just leaving because of the death.
Because of the, what's that?
Because of the death.
Because of the death. Oh, it could just be people leaving. Now, I prefer to think that if they're not here, they're dead. Just, n could equal the number of particles, all right, of like, I don't know, polonium or something, whatever floats your boat. But some kind of unstable particle. Like, I mean, bologna in a refrigerator is in some sense unstable. It ceases to be bologna after several months. You go back to it, it's not bologna anymore, it's something else, right? There's a decay rate there. Although it's hard to count the number of particles of bologna. But anyway, k less than 0. So we have, to be more serious, radioactive decay, right? That's a random process, but the number of particles which decay is proportional to the number there. Can you think of anything else here that falls under this general umbrella of this differential equation?
Maybe how a gas is expanding or something?
Yeah, maybe something. I'm sure there's got to be some kind of gas expanding problem. How about if you have, well, we'll soon see that this is also related to, for example, a discharging capacitor or something like this. But anyway, I'll leave it here for now. How do you solve this? Pretty simple, right? You got dn over n is equal to k dt. Integrate both sides, right? From the final n to the initial n to final n, initial time to final time. This gives us the log of the absolute value of the final number minus the log of the absolute value of the initial number is equal to k times tf minus t naught. Exponentiate both sides, you get the absolute value of nf over n naught. So, the log of this is equal to k times that, right? And then if you exponentiate both sides, you get the absolute value of nf is the exponential of k times tf minus t naught. But what does this mean? I mean, this is equal to what? This is equal to plus or minus nf over n naught, right? But if you think about this, what does it have to be? It has to be plus. Why is that? Just think about it for physical reasons for a second here. So the final n is equal to the initial n times the exponential. If we say tf equals to t, then that gives us n of t is equal to n naught e to the k times t minus t naught. There you go, that's exponential growth, right? Why is it not minus? It's really just a question of nomenclature. But I say that n naught should be n of 0. And if you plug in 0 into that, or n of t naught rather, excuse me. Excuse me. I want n of t naught to equal n naught. So if I would do that, I should choose the plus, because exponential's 1 when we plug in t equal to t naught, right? So, all right. So here's another application. How can we make this more interesting? Things don't just die or live, right? There's some sort of interplay between these things. And so sort of the next model up the chain here is the so-called logistic model. All right? So, do you guys have what you need here? Okay. Excuse me. Science. Sorry, I believe in science. Sorry. Where was it? Oh yeah, so dp dt equals to something like kp. That's exponential growth, right? Now, if you take this, right, and you subtract something like p, oh, I'm sorry, not doing it right. try this again. You got k, p, and then 1 minus p over c. What happens with this formula? I'm supposing k is positive for the sake of discussion. So if p is close to 0, right, the p over c term, and c is pretty big. Just suppose c is positive, k, c greater than 0, right? If you think about it, if the population is small compared to c, p over c is very negligible, right? And so this thing basically grows like dp dt equals to kp in the context that p is small. So it's like exponential growth if the population is small. But what happens if the population goes to c? Right, it gets smaller and smaller, it becomes 0. If the population is over c, this becomes negative, right? So this is a logistic model. The idea of c is the so-called carrying, carrying capacity. And so that's kind of like its stable point. If p is equal to c, that gives you what's called an equilibrium solution, right? So that one we can get pretty easy, right? Like notice, if I have p of t is equal to c for all t, right? Then it's a solution, right? Check it out. If you put this formula in here, you get 1 minus 1, which is 0. On the right-hand side, you get 0. On the left-hand side, what's the derivative of a constant? Yeah, 0. So 0 equals 0, and that's an equilibrium solution. All right, so how do we solve this otherwise? So you got dp over what? P times 1 minus p over c, right? And that's equal to k dt. I separated variables. I guess this might be a Bernoulli problem. I don't know, I haven't thought about it that way. But I can solve it with separation of variables, so let's do that, right? Now this, how do you integrate something like that? Well, let me remind you. If I have 1 over p times 1 minus p over c, that should be equal to like a over p, right? Plus b over 1 minus p over c. What's the algebra I'm doing here? That's called what? Partial fractions. Partial fractions is what I'm doing. Yeah, that's stuff in Calc 2. It's back. Okay, so, sorry. Sorry, it makes me happier than it should. 1 equals to a times 1 minus p over c plus b times p. So you multiply both sides by the denominator over here. That gives you this. And then, plug in p equals to 0. What do you get? 1 equals a, right? Plug in p equals to c. What does that give you? This is 0. This is bc, right? So a apparently is equal to 1. The algebra is really hard here. B apparently is equal to 1 over c. Really tough. All right, so going back up to here, we find out that this is actually equal to 1 over p plus 1 over c times 1 over p minus c. 1 minus p over c. Let me clean it up here. So, in other words, 1 over p times 1 minus p over c is in fact equal to, multiplying through the c here, 1 over p plus 1 over c minus p, right? All right. Oh, that bothers me. Let me put the minus outside if you guys don't mind. Right, we could rewrite this how? How about just minus and p minus c, right? There, I like that more. Okay, now why do I do that? So that we can actually do the integral, right? So, excuse me. Returning to star, we can integrate 1 over p minus 1 over p minus c, right, dp, that's going to be equal to the integral of k dt. If you don't mind, I'm going to, for the sake of just a little bit less writing, I'm going to put a bar here, and I'm saying I'm integrate from time 0. We'll base our solution on time 0 if that's okay with you guys. So from time 0 to time t, and over here from the initial population p naught to p. F, I guess I'll do pf, fine. So what's the integral? You got yourself log p minus the log of p minus c. That, evaluated from p naught to pf, is equal to kt. Of course, this simplifies to what? Yeah, and then evaluate from pf, right? Minus the natural log of I'm not liking this. So let me go a different route. I mean, I could continue down this path, but I think it might be better for us if I back up a second here. And instead of doing what we did, let's try a slightly different path. Maybe easier. Natural log of p minus the natural log of the s value of p minus c is equal to kt plus some constant. I better not use c for my constant. That would be a bad idea. K is also a bad idea. C is carrying capacity. Oh, z. Well, that is out there. I'll use it. Sure, z. There we go. I would not have thought of z. Thank you. All right. So now that we have the constant, this is the log. Oh, I'm sorry. That was horrible. P over p minus c equals kt plus z. And then exponentiate both sides, right? So this is p over p minus c plus or minus, right? Equals e to the z, e to the kt. Okay, so continuing here, that gives me p equals p minus c times e to the z, e to the kt. And I need to solve for p. How do I do that? How about multiply this out, right? So I've got p e to the z, e to the kt, minus c e to the z, e to the kt. I think I still need a plus or minus somewhere. Where should I put it? Because if I put suppose I put the plus or minus upstairs, all right? I can't put it on both. It's either going to the top or the bottom, right? So if it goes to the top, I'll put a plus or minus p there, which means I'll put a plus or minus p where? Here, right? Which means there's a plus or minus here. No, that doesn't. Excuse me. I distributed that over there. Okay, solve for p. What do we got? Curses. Sorry. All right, it looks like I'm gonna move over here if you don't mind. Sorry for this manga style calculation. These things will happen. So I'm trying to solve this equals to that over here. So I've got myself a p times what? Looks like I'm gonna move this over there. So in doing that, that's gonna give me e to the z, e to the kt, minus plus p1 equals to what? Let's see here. C e to the z, e to the kt. And so finally, I get p equals to c e to the z, e to the kt, divided by e to the z, e to the kt, minus plus 1. All right. Now, to make this prettier, what should we do? We basically just keep the c upstairs, divide the top and bottom by, basically e to the z. So what we're going to say is that e to the z is equal to something like, let's just call it alpha. I mean, whatever you want to call it. Just it's still a constant, right? And so this gives me c over 1 minus plus alpha e to the minus kt. There you have it. Took me a little bit longer because it's a little bit harder problem, right? I mean, on the one hand, you got to do separation variables. I mean, you got to do the partial fractions, and the algebra at the end. Actually find an explicit solution is kind of a little fussy. Certainly, we could have continued down this path. I would have used logs of, but I'd had to think about it for a while. I mean, I just think this is more productive. For me, this algebraic route is more productive. You might be successful going down that path, but you know, it is what it is. Now that we have it, let's talk about it. What does it look like? Can I erase the integration? You guys are okay. So what's going on here? As t goes to infinity, what happens? K is positive, right? You have e to the minus infinity here, right? So as t goes to infinity, this does what? This goes to 0, right? So this expression just goes to c. So whether alpha, whether you have a minus or a plus, either case, you're going to eventually go to c. If you got minus, right? Let's see here. I think depending on whether you're plus or minus, you're either going to start below or above the carrying capacity. So the picture of this is something like the following. Oh, you know what? Forget about. Let me actually. We have a projector. Let me show you the picture. I can try to draw it for you, but goodness gracious, it'd be better if I just,
Is that e to the minus c is alpha? Because when you divide by e to the c, wouldn't it be 1 over e to the z?
Let's see here. I'm basically multiplying the top and the bottom by 1 over e to the z, which is alpha, right? 1 over alpha e to the kt. I mean, let's see here. Another way to say this, multiply this, right, by, how to say this, 1 over alpha e to the minus kt over 1 over alpha e to the minus kt. When I do that, oh, you're right. That should be 1 over alpha. Thank you. I'm an idiot. Thank you. There we go. That's better. Of course, that's just a stupid constant, so we might as well just erase it and call 1 over alpha alpha bar or something, right? Anyway, it's still a coefficient. So if you set aside the previous meaning of alpha, my final answer box was still right, but for the wrong reason. So thank you. So yeah, very good. Let's see here. Where is my... This has got to be a... Oh, man. Really? Oh, there it is. You gotta be careful not to pull these cords too far out, otherwise you'll pull over the machine inside the box, and then when you pull over the thing inside the box behind the locked door, that's pretty much game over for the day. So try not to do that. So you guys have a good weekend? Anything exciting happen? I mean, no? Just work? Differential equations homework? No? Let's see here. Okay, come on, let me... I want... Okay. Oh, it's turning on. Well, yeah. right, here's how yeah, I guess maybe I don't have a picture of the solutions in here. Curses. That's when I worked it out in the notes. This is the formula I got in terms of the initial population and the carrying capacity. The formula works out to that through slightly different algebra path. I'll just draw the picture. So it basically looks like this. Here's time, and oh, sorry, wrong picture. So in this case, do we care about negative p? Like, what's negative population? I don't know. Another cool thing, if you differentiate this, right? What's d squared p dt squared? So by the way, this is kp minus k over c p squared, right? So dp dt squared is going to be, what is it? You got yourself a kp prime minus 2 k over c p prime, right? Which is p prime times, there's a k on both, right? So it's kp prime, and that's 1 minus 2kp over c, right? Oh, follow man. I mean Eve. Oh, I'm sorry. Have I offended the women here? It's okay. So we're safe. All right. No, there's no women on the YouTube. Let's see here. Oh no, I shouldn't start this. I shouldn't start this. I don't want to finish it. It's okay. Most of the YouTube controversy is over my inexplicable need to pray at the start of classes. Oh my gosh, can you believe it? He prays at the start of class. Like, that has no place. This is a science classroom. What's that?
Absolute madness.
I know, it is, right? So if you look at this, p prime is going to be positive unless, you can see that p prime is positive what? You can look at it right here, right? This is p prime. So this idea of gaining geometric intuition and understanding of the solution by directly manipulating the differential equation is probably a new idea for you, right? But this is a really powerful idea. This right here, you can look at this and you can tell that the p is increasing if this is positive and that's positive, right? In other words, if the population is what? Less than the carrying capacity, the population is increasing. The only way the population, the growth rate of the population can be 0 is if you're at the carrying capacity. That's the only way this can be 0. So then what is the meaning of the second derivative? Well, second derivative tells you about points of inflection, right? If the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. So when is the second derivative positive or negative? Well, the only place the second derivative can be 0 is basically at this where this is 0, which is what? C over 2, right? So if I make a number line for the second derivative of p, and this is also a number line in the sense of p. It's not a time number line. This is a p number line. That's really different than what we do in Calc 1. Calculus 1, you draw these little number lines or whatever where you're indexing x, right? X is the independent variable. This is a number line with respect to p, right? So p equals c over 2. But if you look at this, what happens? It's going to be negative or positive one side or the other. So like if I plug in the carrying capacity, for example, what happens? Negative, right? And over here it's positive. And it starts at 0. Because past a negative population doesn't have physical meaning. So what I see from this little analysis is that my solution should be concave up from 0 to half the carrying capacity, and then it should be concave down above there. So I can figure out the graph just from that information, actually. It's like here's c over 2, here's c. And so it's got to look something like, what did I just say? Concave up, right? So it's concave up. It's got this, it's concave up right to there. It has a point of inflection as it crosses c over 2. It's going to bend back down. And then ultimately it goes to c. So the solutions have to look something like that. Oh, come on. So like up here, they're just concave down, right? But all roads lead to the carrying capacity. They all get dragged in to C as time goes to infinity. And then here's the equilibrium solution right at the carrying capacity. And that's kind of a typical thing. You have an equilibrium solution that separates you between two like algebraically separate solutions. One with the plus, one with the minus, depending whether you start above or below the carrying capacity. These two different families of solutions. But that's what's called logistic growth, right? This is also not a reasonable model of population growth. There's a fun thing I found in a book, a differential equation book. I think it's in Ritger and Rose, which is a book which was written by a couple of professors at NC State back in the day. It was a popular textbook for a while. You can get a Dover version of this thing for like $2 or $3. It's actually a pretty good book. I used it one year for us in here. Anyway, in this 1920 paper by Pearl and Reed, they suggested that the population of the United States was given by 210 divided by 1 plus 51.5 e to the minus 0.003 t. I believe t is in years, with t equals 0. What is it? What they say t equals 0 corresponds to? Oh, 1790. Okay. So that pretty well matches, 1950. It suggests 151 million. When Ritger and Rose's book was written, or rough draft was written, that was kind of like ballparkish, right? But if you if you keep going, it suggests that the carrying capacity of the United States is 210 million, which is kind of weird since we how many now? Was it 300 or 400? I forget exactly. Well, who knows? Depends on which political party, how many you say, but yeah.
Can you talk about what happens when population equals 0 in our equation? I mean, I know what happened in real life, but does our equation reflect that?
I think that's actually, thank you. That's a good point. P equals to 0 is another equilibrium solution I have neglected. Yeah. That's true. There are two equilibrium solutions. P equals 0. So either this or that factor will make dp dt 0 for all t, right? If you can achieve dp dt equals 0 for all t by a constant solution, then those are the two constant solutions that make this differential equation work for all p. And so technically speaking, you could also find solutions down here. They just wouldn't represent population growth. They'd be something else. So just to give you guys a different example. Sorry, should have told you to take your Dramamine before I did this. Too late. Yowzers. So here's the problem. I like to assign problems like this sometime. Sort of make your own adventure kind of problem, right? So here's the problem. Find a family of curves which are increasing for y less than minus 2, or when y is greater than 2, and they're decreasing between minus 2 and 2. So what I'm saying is, you're looking for these curves, right? They have, what do they have? They have positive derivative before and after minus 2 and 2, and in between minus 2 and 2, they've got negative derivative. So if you think about that, there's a lot of different ways you could do it. But what I suggest is we need the quadratic y plus 2 times y minus 2 to be equal to dy dx. So if you look at dy dx equal to y plus 2 times y minus 2, well, that's exactly what's going to work for the problem, right? Like if y is beyond 2, let's say increasing, let's see here, let's see here, so let's plug in 3. 5 times 1, that's positive, right? If you plug in minus 3, what do you get? You get minus 1 times minus 5, right? It's positive. So this expression's positive. That expression, if you look at it, right? It's a parabola, right? With like 2 and minus 2, so to speak, and this is y, right? And this is dy dx in my way of thinking. I know it's a weird way of thinking, but there it is. So that's where I came up with this differential equation to satisfy that data. And then you can find solutions, right? Through the usual technique like we just did. Partial fractions. Mathematically, this is the logistic problem again, right? It's pretty much the same math as the logistic problem. And so you do integration, and you get this family of solutions, which will, in fact, be what you want. It's increasing and decreasing just where I said it would be for those values of y. Right? Now, if you just tried to sit down and write down formulas for functions that satisfied that geometric data, increasing and decreasing, above and below 2, do you think you could do it? I'm pretty sure I can't do it. But using differential equations to build a model gives us a method to construct functions with data that we want, And then here's a picture. This is the D field or p-plane that I still have Java problems with. But you guys, if you have access to MATLAB, if you can use the p-plane tool, you can create these kinds of things. This is actually a picture that's numerically generated for that differential equation. As you can see, they're increasing above and below y equals 2, and they're decreasing between 2 and minus 2, right? And there's equilibrium solutions at minus 2 and 2. And these little things, that's just where I've clicked. The way p-plane works is it sets up a plot for your differential equation, and then you can click on it, and it'll trace the solution that goes through that point using a numerical technique. It's very, very useful to analyze differential equations. All right. So here is, I'm gonna show you this, and then we'll work some. But I wanted to do this while I have this out. Actually, I'm gonna do one more while I have this out before I write more. So what's an orthogonal trajectory? Like down here, I have pictures of orthogonal trajectories. So we're given x squared minus y squared equals to 1. That is what? That's a hyperbola, right? So x squared minus y squared equals to 1 is actually what in this mess? Think about it. Y equals 0, what do you get? X squared equals to 1, so x equals to plus or minus 1, right? So that is something like this guy, roughly speaking. Something like one of these sideways opening hyperbolas is x squared minus y squared equal to 1. So sorry, this picture's a little bit too busy for my purposes. I mean, it's great in one sense, but it's bad in another. So this is a horrible picture of x squared minus y squared equals to 1, right? So the orthogonal trajectories to this are curves which intersect it at right angles. So it's, these sorts of things. I won't try to extend them, but it's, these go on, of course. But the orthogonal trajectories meet the given curve at right angles. Orthogonal just means perpendicular, right?
This is when y is equal to 0, right? Or is this...
Now, finally. I give up. Let me put this away. Here's a picture of orthogonal trajectories, though. They're nice, and like the reciprocal function, this is like 1 over x, is crossing the x squared minus y squared equals to 1 in a perpendicular fashion. Let me show you how that goes. Stop presenting media, yes. Go away. Here, I'll take a breath and start from scratch here. We have till 1, right? You guys aren't really listening to me anymore, are you? Okay, that's good. Okay, so I'll spend the next probably 10 minutes talking about orthogonal trajectories, all right? Past that, there's still a number of applications I'd like to show you guys. Newton's law of cooling, of course. There's the mixing tank problems, right? Like you have a well-mixed tank and you add salt to it at a certain rate and then water drips out of it. Like, you can find the amount of salt in the tank at time t. That's a differential equations problem. We can solve that. with the techniques we know. I should probably show you how to solve the falling chain problem at the end of class today, since I've got this here. You can solve that. Like, suppose you have a mess of chain sitting on a table, and then it started falling off. How fast would it fall to the ground, assuming that it doesn't have any friction on the table or anything? It just kind of falls off a bit at a time, and then whatever's hanging pulls the rest down. How fast does it fall? We can solve that as a differential equation problem. This is a little bit more. Well, this is much easier than that. So this is the problem of orthogonal trajectories. So this is like a standard, it's sort of a meta example, right? It's an example of examples. So here's basically the task. You're given a curve, or you could even be given a family of curves. All right? And then you're asked find the family of curves which intersect the given family or curve at right angles. Let me use some color coding here just to illustrate what's going on. So the given family, let me say our curve is like this, all right? Maybe there's a couple of them. And what you're looking for then is another family of curves, I'll make it purple, that when it intersects, I can't draw worth anything. These points of intersection, right? Let me try again. Right angles, all right? And of course I mean right angles for the tangent lines, right? So if you drew little tangents here, like this, those would meet at right angles, okay? So you're given the black lines, you're trying to find the purple lines. Yeah.
This sounds vaguely like the gradient function. You're trying to find all vectors perpendicular to the surface.
That's a good point. If we had these were described by, say the given family was given by f of x comma y equals to to some constant, then the purple ones, if we describe them as level curves, say g of x comma y equals to some other constant, say c2, what would the relation between the gradient of f and the gradient of g would be these guys, right? And the gradient of f points off the level curves of f like this, right? And so, yeah, I mean, that's one way you could look at it, is you need that the gradient of f dot the gradient of g is equal to 0. That is, in fact, one way you could look at it. It's not the way I usually attack it, but that's a nice comment, I think. Okay, so let me go back to the one I had projected. So we had x squared minus y squared. And I'm going to raise the ante a little bit here, put a c over here. That's a family of curves. So as c varies, right, you get different things. So c equal to 0 gives you these guys, right? I tried. You should never draw the axes before you draw the curve. It's just a bad idea. But anyway, there's c equals to 0, y equals plus or minus x, right? And then otherwise you got these guys that I'm drawing badly. But hyperbola is either opening sideways or up and down, depending on what. So like over here you got c greater than 0, down here you got c less than 0. These two buckets, and then like the asymptotic one, c equals to 0 is y equals to plus or minus x, right? So there's a given family of curves. Hyperbolas and their asymptotes. How do you find the orthogonal trajectories? So excuse me. Oh, good grief. So another way to look at this, and I like that way, but another way to look at this is that this is like y equals f1 of x, right? And the purple is what? Y equals f2 of x, right? So how should df1 dx be related to df2 dx? If their tangents are meeting perpendicularly, how the slopes are related? I give you a line with slope 2. What's its perpendicular? Bisector have slope what? -1/2, but yes. So -1 over df2 dx. You got to put a minus in there, right? So that's the relation between the derivatives, right? So here, I can figure out what? This tells me what? Differentiate implicitly. You got yourself 2x minus 2y dy dx equal to 0, right? So therefore, dy dx is equal to what? X over y. So this is the given family's ODE, right? So that's given, right? I'm trying to find the family of orthogonal curves, so what do I do? Yeah, the orthogonal trajectories must solve, what do you say?
y over dx equals negative y over x.
Right. Of course, that's based on, this idea, that the reciprocals have to be negative slopes. You could also derive it from looking at the Pfaffian forms of the purple versus the black curves in this orthogonality condition. The same result comes out. But focus. So then we can solve this. How do we do it? You got yourself dy over y equals to minus dx over x. Integrate both sides. Got yourself natural log the absolute value of y equals to minus the natural log the absolute value of x plus a constant. And then exponentiate that thing, right? Well, not yet. Properties of log, that's what? Natural log of the absolute value, 1 over the absolute value of x, right? Using properties of logs. Properties of logs important here, right? Still matter. Partial fractions still matters. Everything you've forgotten from calculus still matters. Everything you've forgotten from algebra still matters. Series and sequences don't matter. Series do matter. Okay, so we don't do anything with sequences particularly. So there's some good news. Sorry, I'm not trying to be depressing. I will help you with whatever you forgot if you just ask me. Anyway, so solve that. Exponentiate both sides. What do you get? Y equals to some constant, let's say k, divided by x. You exponentiate both sides, that would give you like e to the plus or minus the natural log of the absolute value. Here's the steps I'm skipping, sorry. Absolute value of y is equal to e to the natural log of 1 over the absolute value of x plus a constant, which is equal to e to a constant divided by the absolute value of x. And so that implies that y is equal to plus or minus e to a constant over the absolute value of x